All right, today's the last entry in the series of QOSF, what not to do, and today is um, just a slight modification to something that we've actually done already, which is weighted MaxCut QAOA. So I won't go over a lot of the details of QAOA here. I already have talked about that in the past. But remember, we're trying the algorithm of QAOA is an approximate optimization algorithm for combinatorial problems. So it starts off basically with your set of qubits here, and you have alternating layers of cost and mixer Hamiltonians, each with a parameter that you are trying to optimize. So there's in total 2L parameters, which is where L is the number of layers or the depth. And so for MaxCut, we can look and see, okay, well, we want to partition. We set each of the qubits to be one of the nodes of a graph, and we want to partition the graph into two sets such that you look at the most likely measurement set, and that will be the set that results in a MaxCut. And so let's consider a simple example, right? If we have this little board graph, we can see that this is 0, 1, 2, 3. Those are the node indices. We can see that an example of MaxCut, right, would be you could go like that or something, and then you could have so you would have 0 and you would have 2. And that's what you want to measure, right? So with weighted MaxCut, each of these edges have some sort of weight that we want to consider, and we want to maximize that weight too. So it adds just a little bit of trick to it. So let's remember that the cost Hamiltonian for MaxCut is see if I can write this down correctly. 1 minus, and these are for the two edges. 2, and the mixer is usually both theta c, and so this converts into c naught r c naught. This converts into rx to beta. So now we need to think what cost function works for weighted MaxCut. And so this is a pretty straightforward. We can see that since we set it up as a minimization problem, this cost, which I'm representing by this function of z here, but we don't have to do that. It's whatever the weight is, right? So maybe I should start over, right? If we're looking at this function, right, how do we get the cost of this, which we're trying to minimize? Well, we can see, okay, if we know the graph, we can check all the edges, for example. So cost is going to be for every edge. This is unweighted. If you cut this edge between two nodes, that costs you nothing, right? There's 0 cost. If you do not cut this edge, that costs you something. So that results in -1, sort of. excuse me. That's the other way around, right? This would be -1. This would be 0. I'm sorry. I did that in the reverse order because, right, we want to minimize it, and so this is saying this is actually a reward. Cutting it results in a reward. Sorry, I had formulated it as a maximization problem in my head, so that's And the reason we do minimization is just because everything is designed to minimize. You can maximize a negative, it would be the same. And so weighted, right, would be, okay, if we don't cut it, the weight has no impact, right? This still is 0. This doesn't change. But if it's weighted here, this reward is dependent on the weight of that edge. And so we can see, okay, if we want this cost, right, it'll be the weight of the, suppose we have some edge, ij, and we want to multiply it by something. And so this is where, this is my expression for it. We have 1 minus 2. And so this is z on I. This is 1 minus 2 z on j. And this is minus 1. So let's think about what this means, right? We're measuring in the computational basis. So if we measure some set, some numbers, right? Maybe it's 1, 1, right? This means that these two are in the same set. So if we iterate over all the edges to check the cost function, if there's an edge between these two and they're in the same set, then they haven't been cut, right? Definitionally, since, if you have like, let's consider just this simple 3 graph, right? If we just cut this right here, we make it slice right here, and we can see that, let's suppose this is 0, 1, 2. We'll therefore expect to measure either 1, 0, 0 or 0, 1, 1, depending on how you encode this. These are the same thing, right? This represents one set and this is the other set. And so we can see we want both of these to have the same cost. So we want zeros and ones to be equivalent, and we can see that this has some, this and this have some cost because they're both uncut edge, right? You didn't cut this edge, but you could have cut it. So there's a cost there. So if we expand this out, we can see why. So we can do weight. We have 1/2, 1 minus 2 z. I'm just going to drop the z, by the way, but know that it is there. J minus it's plus 4 ij minus 1. So we can reduce this down to weight times negative theta I minus j plus 2 ij. So let's consider the possibilities, right? There's 3 possibilities. Either they're both the same and they're both 0, they're both different and they're both 1, or sorry, they're both the same and they're either 0 or 1, or they're both different. So if they're both 0, we can see real quick that this is 0, this is 0, this whole thing equals 0. If they're both 1, then we can see this becomes negative 2, this becomes 2, so this equals 0. And so that's what we're trying to say, right? Is if if you don't cut them, you don't get any reward, right? You can also frame this as saying if you do cut them, you get a punishment, so that you could minimize the punishment, maximize reward, whatever. But we can say if you don't cut them, you don't get any reward. You're not cutting anything. Remember, we're trying to max them. We're doing the max cut problem. We want to cut the number of, or in this case, weighted max cut. We want to cut the most weight. And so you get no reward if you don't cut something. And so now we can see if one is 0 and the other is 1, this term becomes 0 and this term becomes negative 1. So this will become negative weight. And so then we can see, well, that's what we want to minimize, right? We want to cut as much as we can, or as much weight as we can. And so that's pretty much the basics of the problem. That's really all we need. So we can get straight into the code right away. I guess I don't really need, I don't think I used the math function. Delete that. So we can create a random graph here. And we can see that in this case, I'm just creating, you could do some there's a lot of different ways you could create the graph, right? But I'm just doing the Erdos-Renyi graph. So that means there's every edge is picked at some probability defined, 0.6. And then I pick a random weight between 0 and 10. Maybe I'll make it 0 and 1 to make this easier. Otherwise, so we can do the unweighted version. It's the same code, right? Just the weights would be 1 in every case or some constant. And then we set the edge weight to that random weight. You could, do some sort of heuristic here if you wanted to. We define the depth of the circuit. So this is the number of alternating cost mixer Hamiltonians. We define certain repetitions. This is how many times we measure it. And we define the qubits, which is 1 per node, remember. So first we initialize it to the complete superposition by applying a Hadamard gate. So we take the circuit and apply a Hadamard gate to every qubit. Now we have the cost unitary. So remember, this is equivalent to the C0 targeted on the first, controlled by the first, targeted to the second, and then RZ on the second, followed by a C0. And this is just standard practice. You'll notice this is also in the QAOA, TensorFlow QAOA video, that this is a, when we exponentiate what we wanted, this is exactly what we got. Then the mixer is Rx of 2 times the parameter. So that just defines each layer, right? Pretty straightforward. So now we create the circuit. So we have create the gammas and the betas. So the gammas are for the cost Hamiltonian, the betas are for the mixer Hamiltonian. We initialize the circuit, we do alternating cost mixer applications. Also, one thing I should mention before I go too far is this code was inspired, I guess. I used a blog post code as a starting point because for the task application they gave you some starter code, and so I used that starter code that comes from some blog post that I'll link down below. And so now we measure 1,000 times, and so we split it, and so this says results is now a length node array, where the first row represents all the values measured by the first qubit. So it'll be 1,000 length in this case, and then so it's a node by 1,000, I guess, list, and so we can iterate and convert that into the measurements that we want, which is we want each individual one. So if we have some long thing, right, we would want this to be so if we have 4 qubits, right, we would want this to be something like that. And so we can do this conversion here, and that's all that code does. And now, excuse me, we can create, for the cost function, which we are trying to minimize, remember, we can create the circuit. Why there's so many range zeros? We can, and then we can go over the edges and get the total cost here, right? So for every measurement we made, because we're averaging out to get the probabilities of measurement, basically, right? We get the weight, and this is the exact formula that I showed before. We multiply by the weight, and then we divide by the total number of repetitions, and this is what we're optimizing, right? So we can see down here we use Kobola, and notice we start at a random initialization, and so you'll see in the code that it's important to have multiple random initializations because there's some pretty high variance in the ultimate outcome. And so then we iterate over 8 times, optimizing each time, and if it's less than optimal, then we or if it is the new optimal value, then we replace it. And then we can see this is the exact same code from the TFQ example where we say, okay, let's create the circuit. Now we can sample the circuit and get the results, and then convert them into this format. And then we can see, okay, let's generate the real example, right? So we say we get all the possible weights, MaxCut weights for the graph, because we can just brute force it at this size. And then we get all the possible, we get all the results from the quantum predictions. And then we can find out the result. So for example, we can run this code. I already have an example up here. This is for nodes 8. Zoom in a little bit actually. So you can see there's a pretty, there's a high variance, right? -49 to -58. That's pretty big. That's a substantial cost differential. And so that you can see why it's important to do this many times. And we can see in this case it achieves 0.7769. So now let's go back to the code and let's just make this deeper. Let's do depth 6 instead of depth 4, because that was depth 4. And now we'll run the code, and I will just pause it here because it takes a little bit to run. Okay, I finished running. So you can see here, this is the 6 layer, and this is, I reran it with 8 layers. So you can see on any given run, there's a fair amount of, statistical fluctuations. So it may not always increase perfectly, but you can see it does get better with more layers. You might be wondering why the cost is lower, and that's because I changed the weight from 0 to 10 to 0 to 1. And so, yeah, that is the code for a weighted MaxCut QAOA and just Cirq. So, yep. And that's also the end of the QOSF series. Do not know what will come next, but I do know that I'm sure I will find more things to distract me from the ICLR workshop submission that is due now in, let's see, 36 hours that I have not started. So I'm sure I will do many things to distract myself from that. But I do not know what will come next yet.